Thanks, Zoe.
Jenke, the floor is yours.
Thanks very much, Zoe. And thank you very much, Hannah, and the other organizers as well for this conference. I'm very much looking forward to the in-person conference next year as well. And thank you for inviting me to speak today. So I'll be speaking about my last main project of my PhD that I did at the University of Edinburgh in the group of Julie and Michelle, together with Mark Mackey from Cresset. And this is all about network planning and free energy calculations. I'm quite excited to see that the next two speakers kind of work in the same theme as well, especially because I did this for the last 2 years, so very fun to see. And right, so of course, all of you know this, that free energy calculations are a very helpful tool in early stage drug discovery, mostly in aid of the ligand optimization problem, where we have a fixed scaffold and we're trying to find R groups that increase the binding affinity to the therapeutic target. And at the core of this whole methodology sits the thermodynamic cycle, where again, most of you will be familiar with this, but it's good to kind of drill it down for just a second, where instead of computing the delta G bind directly for our ligand to the host, what we do in relative binding for energy calculations is we transform ligand A into ligand B, both in the solvated phase and in the bound phase, and we subtract those two free energies to get the relative binding free energy. So this is important to note because in RBFE, we actually talk about transformations, right? Ligand transformations. And if we have a ligand series, we need to pick what transformations we do between the ligands. So if we have 5 ligands, for instance, this is quite simple, of course. And we could, for instance, say these 5 edges are the edges that we want to do molecular simulations for, and then we end up with the delta G bind values for those particular edges. Of course, in communication with medicinal chemists, etc., we're more interested in a per ligand prediction. So we have a variety of algorithms available. We usually do a weighted least squares regression to come to a per ligand relative binding affinity. And the weights here just refers to how we weight our regression while taking into account the noise per edge. So how do you actually make a graph? It's a seemingly simple problem, but it's actually quite complicated. So for 5, you can draw it by hand, but the number of possible graphs increases quite a lot if you have more ligands, right? So for instance, if we have 16 ligands, which is still quite a very small ligand series, we have 2.7 to the power of 16 possible minimally connected graphs, which isn't even what we would want, because normally we'd want to have some cycles within the graph as well. So there's many graphs to choose from, but what we want to end up with is a graph that has a sufficient number of edges that we can do simulations, that we can trust the prediction outputs. But we don't want to do all of the edges because that's just too much simulation time, which isn't ideal either. So in practice, how this usually works is there's an algorithm behind the screens, and LOMAP is one of the state-of-the-art ones. Cresset's Flare FEP engine uses LOMAP behind the screens. And the basic principle of LOMAP here is that for a ligand series, we compute the LOMAP score for all possible edges within the series. And that score models the likely reliability of that edge. And then obviously, we kind of filter down all of the edges, and then we come to a graph that we like. So that's the simulations that are actually being run. And that LOMAP score really depends on kind of how similar particular R groups are to each other, as well as a number of rules that have been set by experts. So there are 2 main kind of problems or challenges in this kind of workflow, of which the first is the one that I'll be talking about, which is coming up with a good metric to model that expected reliability of all edges. And then there's coming up with the actual shape of the network, which, at least in my mind, is the main theme of the 2 next talks. So there's definitely a big advantage to this approach, which is that it just works quite well. So over the years, the low map score, especially the rules, at least in the case of Cresset's flare, have been developed to really be a tailored fit for the shortcomings in the FEP code, the RBFE code. A major limitation of this approach, though, is because we have all those rules that are tweaked for the RBFE code, we have limited transferability to other RBFE codes. So if you would want to do this with Amber, for instance, you would come into trouble because the rules just don't apply necessarily. So instead of low map score, an ideal metric could, for instance, be the inaccuracy. So the delta G offset, and this is something that we've worked before in our group as well, which is very simply just the difference between the free energy prediction and the experimental value. So it's just the mistake that's been made. But neither are known a priori, right? So you wouldn't really know all of those values for all of the possible edges in your ligand series, because you would have to compute all of the edges before you want to choose which edges you want to simulate, which doesn't make any sense. And then you'd also have to have the experimental binding measures, which you don't always have either. But you would have a near perfect graph in this case. A more realistic measure would be to look at the precision, which is what we've done in this work. So the uncertainty of free energy calculations, expressed as just a standard error of the mean of a quintuplicate. And we know that this is correlated weakly to the actual offset that I talked about in the last slide. And here the advantage is, of course, that we don't need the experimental data a priori, but we still need to do all of the simulations for the fully connected network. So in this project, what we wanted to do was find a machine learning model or develop a machine learning model that can actually predict these SEM values, these precisions, and then feed those new predicted SEM values into the low map algorithm, and then have the low map algorithm, instead of using low map score, figure out the graph based on those predicted SEMs. Advantages here would be that we can do all of these simulations in advance and train a model on that, of course. And it does not require expert engineering, so it could be more transferable to other RBFE codes. So to do this, we built a representative training set. We looked at all of the publicly available benchmarking series out there, and then we checked which transformations are actually possible within each series. And then we took all of those transformations, and then in this example on the left here, so there's dechlorination and fluorination at the same time, we grafted that onto a single scaffold, a benzene. And then after removing all of the duplicates, we ended up with about 4,000 transformations. And we feel that that is a representative set of all of the transformations that you would ever want to do in RBFE on a common benzene scaffold. And the reason we do this is because then we don't have to cover a very wide chemical space of the ligand scaffolds, if you will. So we know that this actually loses some data, but not all of it. So you can see this, for instance, this chlorination on this end. This is just an example, but these are just derivatives in RBFE space on the x-axis. On the y-axis, we have the original scaffolds, the original ligands in the actual complex as well, so delta G bind. And we can see that there's a weak correlation here. We wouldn't have expected it to be perfect, just because we've removed a lot of information. Right? We've gained a very transferable training set, however. So I don't really have time to go into the machine learning model, but the takeaway here is that we have a graph neural network, which is kind of a Siamese neural network type design that has a dual input, and the output is a single node with just a regression output. And then we've trained with the transfer learning approach, where we used a cheaply computed label to have about 1 million points to pre-train the model. And then we've transfer learned that onto our RBFE space in order to learn the SEM values to be predicted. So for a test set, we with the trained model, we wanted to train on test on TIC2, which is a very commonly used benchmarking series. This is just a basic methodology. So what we did for TIC2 is this has 16 ligands, and what we actually did was we simulated all of the edges. So 16 ligands, 240 edges. So we simulated 120 edges, just the one direction, 5 times, which was a reasonable amount to compute. And then that actually gives us a lot of room to play around in. And what we can do now is we can give any input heuristic, so low map score, for instance, or predicted SEMs, put that into the low map algorithm, look at what graph is generated, and then compute the per ligand estimated binding free energies and compare that to experimental values. And then we can see which graph generators are better than the others. So looking at the controls first in highlight, so we have a negative control here, which is the ECFP6 similarity between the original scaffolds. So this is just the TYK2 original ligands, and then just the overall ligand similarity, which is a fairly crude way of approximating the reliability of an RBFE transformation. So we have a positive control as well, because we did all of these edges, right? And we have all of the experimental binding affinities. We can actually compute the delta G offset for all of these edges and use that as an input to low map to come up with a graph that is very, very accurate, as you can see, at least for this amount of sampling. So moving on to the actual main results. So bottom left here, we have the low map score, which is the state of the art that we discussed previously, based on those rules that I told you about. And then we have our model that with our neural network that predicts the SEM values. And you can see that those graphs, even though they are slightly different, they perform more or less the same. Looking at the statistics on the right, I'm just going to focus on the Pearson R, but the patterns are more or less the same in the other metrics as well. We can see that for the gray bar on the right, our positive control is by far the highest, whereas in purple, we have our ECFP6, which is really quite low as a negative control. Then in between, we have our model in brown, and then we have low map score, so the one that the state of the art that we compare against in pink. So you can see that they're pretty much equal. So one other, in my opinion, really quite interesting thing that we did in this work was we looked at star-shaped networks as well. So you can see it in this bar graph already. The second from the left, the orange bars, you can see that we have done star-shaped networks, and these are actually quite commonly used, especially in industry where, you know, if you have more than 50 ligands, it's actually quite difficult to generate a network for these. It's just too costly and it just doesn't work quite well. So people typically take a reference ligand, typically just the lead that is to be optimized. And then all of the other ligand series are just connected with one single edge to that hub, if you will. So hub and spokes is kind of what it looked like. But this is, of course, a very crude way of generating a network. And we wanted to see if, at least for TYK2, this was or would have been a good idea. And it turns out that it really wouldn't be. So this is a bit more data on that. So I'm just going to focus on the right-hand side here, where we compared it to random, right? So for TYK2, 16 ligands, there are, of course, 16 possible star-shaped networks because we can take 16 different hubs. And the vast majority of them actually perform about as bad as random models. And of course, in this case, because TYK2 is a very small series, only 16 ligands, even a randomly generated network. So with that, I mean, generating a network with, instead of low map score, we use random floats. Even a randomly generated network sometimes will be decent, right? But it's interesting to see that the star-shaped networks are usually not better than the randomly generated networks. And in fact, there is only one that is just really slightly better than randomly generated networks. And that is the one that you would expect in TYK2 if you know the series, which is there is one single kind of smallest ligand, which is basically the MCS or the scaffold of the rest of the ligands. And it, at least for our RBFE code, which is single topology, that works best in terms of transformations. But it's food for thought that maybe on a larger scale, a star-shaped network might not always be the best idea. But this is, of course, quite difficult to test in practice because you'd have to do a fully connected network analysis like we did, which is really quite costly for more than 50 ligands. So conclusions, I think there are three main outcomes here. We have generated RBFE space, which is a publicly available training set for anyone to use. And I think that there could be a variety of other applications to this data set as well. We have made a Siamese neural network implementation for RBFE, and we have recently uploaded this as a preprint, and you can read more about the methodology in that preprint if you're interested. And then finally, we have created a network generator that is competitive with the state of the art, with the added advantage of being more transferable. So I have actually concluded, or almost concluded, my PhD with Julian, and I've since 2 weeks now have moved on to do a postdoc with John Kudera, where I will be doing free energy calculations in project support for ASAP discovery. So this is my new email if you ever want to reach out to me for this work or for any other work. And with that, I would like to thank you for your attention, and I'd be happy to take any questions.
Thank you. Thanks very much for the really nice presentation. I want to remind everyone that you can write in the Q&A. I want to ask Jonah also if, because it says here that only hosts and panelists can see the questions, but that was not the case in our previous meetings because everybody could see the questions. So it would be nice if everyone can see the questions. Maybe there is a setting that you can change. But until then, please send us the questions. I don't see any question now in the Q&A button, but I have one. So I didn't. Oh, okay, yeah. Right. Okay, there is one question which just came in. Have you compared transferability of your score versus LOMAP score?
We've not. It's really quite difficult to compare transferability anyway. So I know that I say that is an advantage of the approach. However, if we want to show full transferability to another RBFE code, we'd have to rerun the simulations for RBFE space with another RBFE code altogether. Because if we want to retrain the model, and that would make it transferable to another RBFE code, we would have to run all of those simulations first. So that's very interesting for the future, but we're not quite there yet. And at that point, if we start doing that, then yes, of course, LOMAP score in its current form anyway will be tested as well. I know that OpenFE, they're testing with LOMAP as well. And it's very interesting for them, of course, to strip down all of the added rules to see, how good the networks look at that point and then build from there.
Daniela asks if you try to use fully connected graphs and whether it is a good way provided that we have enough computational resources.
Oh, that's a super good question, actually. So yeah, we tested this fully in the assumption that it would be amazing predictions, and they weren't. So that's really cool. So for Take-Two, because we had done the whole network, right? We thought, why not estimate the per ligand binding affinity? And it was quite poor, and it was a bit puzzling, because in theory it should obviously be the best one. But this is just because in the weighted least squares analysis anyway, it hasn't really been built to accommodate that many edges coming into a single node. So we think what's happening is that there are some very, very noisy edges coming in, and the weighted least squares analysis just doesn't quite ignore them as much as it should, right? So they introduce noise to the whole network, and then that messes up their prediction.
Okay. And one last question from Torsten. How many different target classes have you used to develop and validate the approach? And are certain target classes that perform better or less well?
Right. So we, in terms of test set anyway, we've tested TIC2, of course, and we've tested TNKS2 as well, because we did want to have a second kind of test set on the side. So we report on this in the manuscript. Just going through all my backup slides. There we go. So this data is reported a tiny bit differently, but the main point is that after 5 replicates for each of these sort of standard statistics, we end up more or less in the same range. I didn't quite mention this in the talk just because there's a lot of kind of ideas behind this particular test set. I think with this kind of work, we want to stay within the benchmarking series.
So
That's your main question.
the data set is available. Is it online also on the GitHub?
Yeah.
Okay,
Yeah.
that's great. There is one more question by David, but since we have to move on, you can type in actually the answer to David because he has a couple of questions. And for all the speakers, you can type in the questions to the the answers to your questions. And also for the attendees, you can still keep typing in your questions because our speakers will be able to type in the answer. And with that, I'd like to thank Jenke and proceed